In this video, I want to give you a general introduction to the remainder theorem and how it applies to polynomial functions. Well, the remainder theorem states, if a polynomial function p of x is divided by the linear binomial x minus k, then the remainder, r, is going to be p of k. Well, what does that mean? Well, we're going to look at this example here. We have p of x, and it equals this polynomial function. And we're going to also discuss and look at the linear binomial x plus 3. Okay? And if we divide this polynomial, p of x, by x plus 3, the remainder will be the same as if we were to just take the k value and evaluate the function there. Okay, well maybe that didn't help any more for an explanation, so let's go ahead and do it so you can see it worked out here. So we know that the linear binomial needs to be in the form x minus k. Okay, so this x plus 3 is actually x minus a negative 3. So this k value is, well, negative 3. So a couple of things are going to happen. First of all, I'm going to go ahead and evaluate my polynomial function p at that k value, negative 3. Okay, and then I'm going to go ahead and use synthetic division, and I'm going to divide using this k equals negative 3, and I'm going to show you the relationship. Okay, so let's start by evaluating this function. So we have 6 times, and that'll be negative 3 to the 4th, minus 33 times negative 3 squared, plus 48 times negative 3, minus 40. Okay, so it'll be 6 times, looks like 81, minus 33 times 9, plus 48 times that negative 3, and then minus 40. So going ahead and doing the arithmetic here, it looks like 486 minus 297 minus 144 minus 40. And when I subtract all these, I'm going to get 5. Okay, so kind of just tuck that number in the back of your mind. Let's go ahead now and use synthetic division and use negative 3 outside here for this k value. And remember, synthetic division concerns itself with the coefficients and constant of the polynomial function, which we had right up here, which you can glean those values from the evaluation here as well. Okay, so it's going to set up this way. 6 was this leading coefficient. Our cubic term had a coefficient of 0. Our quadratic term, our linear term, and then our constant over here. And I like to put this box here for my remainder. Okay. So let's go ahead and do this synthetic division. So I'm going to bring this leading coefficient of 6 down, and I'm going to work through a series of multiplications and additions. So negative 3 times 6 is negative 18. When I add that, I get negative 18. Multiplying here gives me 54. Adding gives me 21. Multiplying gives me negative 63. Adding gives me negative 15. Multiplying 45. And finally, this final addition gives me 5. Well, okay, well this was 5, and this was 5. So what we said using this remainder theorem was, when I go ahead and do this using synthetic division, whatever I have for this remainder is going to be the same value I get when I evaluate the function at that value of k, which you'll see was, yes, 5. So these values were the same. Okay, well, it seems like maybe it was a coincidence or maybe not. I don't know. I mean, there's a theorem based on it, so I imagine not just a coincidence. So let me go ahead and show you a different approach. And you can see why it works the way that it works. Okay, so we're going to go ahead and still use the same function, p of x, and that'll be that 6x to the 4th minus 33x squared plus 48x minus 40. But instead of using a numeric value, I'm just going to use the general x minus a factor, which means that that k value is just a. So we'll start by evaluating it p at a. And really all we're going to do here is just replace all these x's with a's. Okay? And let's go ahead and keep keep a hold of this expression right there. He's going to be important. So then let's go ahead and do synthetic division and just use the a right here. And I'm going to extend this a little farther because we're going to need some more room horizontally. So here is our 6, our 0, negative 33, 48, and negative 40. Okay, so we just have the a here. We're not using a number, but that's okay. So bring down the leading coefficient and multiply. So 6 times a. When I add, I have 6a. So multiplying will give me 6a squared. Adding will give me 6a squared minus 33. Multiplying by a, I'll multiply it to both of those terms. So 6a cubed minus 33a. The addition here is 6a cubed minus 33a plus 48. And then finally, multiplying all three of these by a will give me 6a to the fourth minus 33a squared plus 48a. And adding these up, and yes, here's my remainder. We have 6a to the fourth minus 33a squared plus 48a minus 40. And lo and behold, this expression right here, which I have for the remainder, is the exact same expression I had when I evaluated the function at a. So this is why we can say that the remainder is going to be the same as what I get when I evaluate the function right there. And you can see all I've done is through this series of multiplications and additions, I have just built up the powers of a. So that's 6 multiplied by a once, twice, 3 times, 4 times, and that's how I had the 6a to the fourth. So that's kind of how that synthetic division works, running that number through. Anyway, so to recap, we know that the remainder theorem is going to have the same values when I either work the division using synthetic division, looking at the remainder, or if I take that k value and evaluate the polynomial function at k. So this is going to be useful later on when we're trying to use like the rational root theorem, or when we're trying to factor large polynomial functions and maybe we're not sure what factors work and what factors don't work. So it's going to be a little bit of a shortcut and it's going to help us out. So anyway, there's a general introduction to our remainder theorem.